Welcome back to Strindberg Space Stories. If you're new here, this is a place for long, quiet journeys through the science and mystery of space. No rush, no noise, just you, the dark, and a story worth thinking about. If that sounds like something you'd enjoy, consider subscribing. It really does help others find their way here too. Tonight we're going somewhere strange, not to a distant galaxy, not to the edge of the observable universe. We're going to a moon. A small, ice-covered moon, barely larger than our own, orbiting the largest planet in our solar system. It is one of the most studied and least understood worlds we know of. And beneath its surface, sealed under miles of frozen silence, there may be an ocean that holds the answer to the oldest question our species has ever asked. So settle in. Let your breathing slow. You don't need to do anything at all. Just listen. Imagine, for a moment, that you're standing on the surface of Europa. You arrived somehow, impossibly, and you're standing on ice. Not the kind of ice you find on a winter lake. This ice is ancient, harder than concrete, compressed by its own weight over billions of years. It is stained in places with a brownish-reddish tinge, salts and sulfur compounds altered by the relentless bombardment of radiation from Jupiter's magnetic field. The ground beneath your feet is scarred with long, dark lines, some of them hundreds of miles long, cracks that crisscross the surface like veins on the back of an old hand. The sky above you is black, not dark blue, not dusky. Black. Europa has almost no atmosphere, just the thinnest wisp of oxygen molecules, too sparse to scatter light or carry sound. If you shouted, you would hear nothing. If the ice cracked beneath you, you would feel the vibration through your boots but hear no sound at all. The silence is total. It is the most complete silence you have ever experienced, and there, filling nearly a quarter of the sky, is Jupiter, enormous, swirling, a wall of amber and cream and rust, its cloud bands slowly churning, its great red spot staring down like the eye of something vast and indifferent. Jupiter does not rise or set on Europa. It hangs in the same place, always, because Europa is tidally locked, forever showing the same face to its parent. You could stand on this spot for 1,000,000 years, and Jupiter would never move. It would just hang there, filling the silence with its presence, while beneath your feet, miles and miles below the ice, something waits in the dark. That something is water. The story of Europa's ocean begins, in a sense, with Galileo. Not the spacecraft, but the man. In January 1610, Galileo Galilei pointed a telescope at Jupiter and noticed 4 small points of light moving around it. He watched them for several nights, recording their positions, and realized they were moons. It was one of the most consequential observations in the history of science, because it proved that not everything in the universe orbited the Earth. The 4 moons he discovered, Io, Europa, Ganymede, and Callisto, are still called the Galilean moons in his honour. He could not have known what Europa was. He saw only a dot of light. But he set in motion a chain of discovery that, 4 centuries later, has led us to suspect that this tiny dot may harbour more liquid water than all the oceans on Earth combined. For most of those 4 centuries, Europa was simply a name on a list. A small, icy moon, unremarkable among the dozens that orbit Jupiter. That changed in 1979, when the Voyager spacecraft flew through the Jovian system and sent back the first close-up images of Europa's surface. Scientists expected craters. Every solid body in the solar system is pockmarked by billions of years of impacts. Mars has them, Mercury has them, our own moon is covered in them, but Europa was different. Its surface was white and smooth, crossed by a web of dark lines, but almost entirely free of craters. This was deeply strange. It meant the surface was young, perhaps only 50 million years old, constantly being renewed by some process from below. And the most likely process was liquid water, rising through cracks, freezing on the surface, and erasing the scars of ancient impacts like snow-covering footprints. The evidence grew stronger with every mission. In the mid-1990s, NASA's Galileo spacecraft entered orbit around Jupiter and made 11 close passes of Europa over the course of 8 years. Its magnetometer detected a fluctuating magnetic field around the Moon, a field that responded to Jupiter's own powerful magnetism in a way that was consistent with one thing and one thing only: a large body of electrically conductive liquid beneath the surface. Salt water, a global ocean hidden under the ice, conducting electricity and generating its own faint magnetic signature. The discovery was quiet. There was no press conference with a bold claim, just data accumulating over years, pointing in the same direction: an ocean under the ice, on a moon that most people had never heard of. The Galileo spacecraft also captured images of the chaos terrain, regions where the ice appeared to have broken apart into enormous blocks, rotated and refrozen as though something beneath had disrupted the surface from below. Some of these blocks were the size of cities. The pattern suggested that warm material had risen from below, softened or melted the ice, and allowed it to shift and settle into new positions before refreezing. It was the kind of evidence that does not prove anything on its own, but that, taken together with the magnetic data and the smoothness of the surface and the patterns of the cracks, builds a picture that is difficult to explain any other way. Europa has an ocean. The scientific community reached something close to consensus on this point by the early 2000s. The remaining questions were about the ocean itself: how deep, how salty, how warm, and whether anything lives in it. For decades after Galileo, one question dominated the science of Europa: how thick is the ice? The answer matters enormously. A thin shell, a few miles at most, would mean the ocean is relatively close to the surface. Cracks might penetrate all the way through. Plumes of water might erupt into space. A lander, equipped with the right tools, might conceivably drill down to liquid water within a human lifetime. A thick shell, on the other hand, would mean the ocean is locked away behind a barrier so massive that reaching it would require technology we have not yet imagined. For years, the estimates range from less than half a mile to more than 20 miles. The uncertainty was enormous, and it shaped every conversation about what Europa might be and how we might explore it. In December 2025, we finally got an answer. A team of scientists published results from NASA's Juno spacecraft in the journal Nature Astronomy. Juno, which was designed to study Jupiter's atmosphere, had made a close flyby of Europa in September 2022, passing just 220 miles above the surface. During that flyby, its microwave radiometer, an instrument that measures thermal radiation at multiple frequencies, peered beneath the ice and measured its temperature at various depths. By piecing together these temperature readings, the team constructed a profile of the ice shell. The result was sobering. The shell averages roughly 18 miles thick, or 29 kilometers, with an uncertainty of about 10 kilometers in either direction. That is deeper than the Mariana Trench, the deepest point in Earth's ocean. It is deeper than the height of Mount Everest, twice over. It is, by any human standard, an almost inconceivable wall of ice. To feel that distance, think about it this way. 18 miles is roughly the distance from the centre of a city to its outermost suburbs. It is the kind of distance you might drive in 20 minutes on a motorway, except instead of roads and houses and trees, there is only ice. Solid, ancient, compressed ice, growing imperceptibly warmer as you descend, degree by fractional degree, until finally, after miles and miles of frozen silence, it gives way to water. If you could drill through it at the rate of 1 foot per hour, working around the clock without pause, it would take you nearly 11 years to reach the ocean. The Juno data revealed something else. The ice is not perfectly solid. It contains cracks and pores, small voids and fractures, extending hundreds of meters below the surface. But these features are too small and too shallow to serve as pathways between the surface and the ocean. They are imperfections in the ice, not corridors through it. The shell is a barrier, not a bridge. Whatever is in the ocean, below is sealed away, separated from the surface by a frozen wall that no known organism and no existing technology could penetrate. And yet, at the very bottom of the shell, where ice meets liquid, there is a quieter, gentler process at work. Scientists believe that tiny crystals of ice form in the supercooled water just below the shell and drift upward, accumulating on its underside like snow falling in reverse. This underwater snow, which has been observed beneath ice shelves in Antarctica, is purer than ice that freezes directly from the surface, because the freezing process tends to exclude dissolved salts. If this is happening on Europa, it means the base of the ice shell may be relatively clean, while the ocean below may be saltier and richer in dissolved minerals than the ice above. The boundary between the two worlds is not a sharp line. It is a slow, patient exchange, measured in millimeters per century. Two worlds, touching, barely communicating, separated by a phase change that takes the span of a human life to move a single inch. Beneath that boundary, there is water. Not a lake, not a sea, an ocean. A global ocean of liquid salt water that may extend 60 miles deep, wrapping around the entire moon from pole to pole. On Earth, the deepest point in the ocean, the bottom of the Mariana Trench, lies about 7 miles below the surface. Europa's ocean may be nearly 10 times deeper, and unlike Earth's oceans, which are interrupted by continents and island chains and mid-ocean ridges, Europa's ocean has no land at all. There is no shore, no coast, no solid ground between the ice above and the rock below, just water in every direction, held in place by gravity, sealed by ice, and kept liquid by forces that have nothing to do with the sun. No one knows what this ocean looks like. No camera has ever photographed it. No instrument has ever touched it. But we can say certain things about it with reasonable confidence. The water is almost certainly salty, enriched with magnesium sulfate and sodium chloride leached from the rocky seafloor over billions of years. Near the base of the ice shell, the temperature hovers just below freezing. Deeper down, where water meets rock, it may be a few degrees warmer, heated by the same forces that keep the ocean liquid. The pressure at the bottom would be enormous, many times greater than the pressure at the deepest point on Earth, enough to crush any submarine we have ever built. And it is dark. Completely, permanently, unimaginably dark. On Earth, even the deepest ocean has a memory of light. The water that fills the abyssal plains was once at the surface, warmed by the sun, stirred by wind, touched by rain. It has cycled through the planet's hydrological system for billions of years, carrying with it traces of the sunlit world above. Europa's ocean has no such memory. It has never known light. Not a single photon of sunlight has penetrated 15 miles of ice since the ocean formed. It was born in darkness, and it has remained in darkness for longer than complex life has existed on Earth. Whatever is down there, if anything is down there, has been waiting in that darkness for a very, very long time. The fact that Europa has a liquid ocean at all is one of the most remarkable things about our solar system. Jupiter orbits more than 5 times farther from the Sun than Earth. At that distance, the Sun is a bright star but provides almost no warmth. Europa's surface temperature hovers around -260 degrees Fahrenheit, cold enough to freeze carbon dioxide, cold enough to make steel as brittle as glass. Everything on Europa should be frozen solid, all the way through, to the core. And yet the ocean persists. It has persisted for billions of years. Something is keeping it warm. That something is Jupiter. Europa orbits Jupiter in a slight ellipse, not a perfect circle, and as its distance from the giant planet changes with each orbit, Jupiter's gravity alternately stretches and compresses the Moon's interior. This rhythmic flexing generates heat deep within Europa, in much the same way that repeatedly bending a piece of metal makes it warm to the touch. The process is called tidal heating, and on Europa it is powerful enough to keep an entire ocean liquid at a distance from the Sun where everything else is frozen. The same tidal forces are responsible for the cracks on the surface. As the ice shell flexes and bends with each orbit, it fractures, producing the lineae and the chaos terrain that make Europa's surface so distinctive. The Moon is being gently, constantly kneaded by the gravity of its enormous parent. There is something beautiful about this. The warmth that sustains Europa's ocean comes not from a star but from gravity, from the simple fact that Europa is close to something very large and very heavy, and that its orbit is not quite circular. The same force that raises the tides on Earth's beaches is what keeps an alien ocean from freezing solid on the far side of the asteroid belt. Gravity, doing what gravity does, reaching across the vacuum, bending the shape of a world, and perhaps without intending anything at all, creating the conditions for life. But Europa pays a price for living so close to Jupiter. The giant planet has the most powerful magnetic field of any planet in the solar system, a field generated by the churning of metallic hydrogen deep in Jupiter's interior. Trapped within that magnetic field is a belt of charged particles, electrons and ions accelerated to enormous energies that would kill an unshielded human within a matter of hours. Europa orbits directly through this radiation belt. Its surface is bombarded constantly, the charged particles slamming into the ice and breaking apart molecules, creating new compounds including oxygen, hydrogen peroxide, and a range of irradiated salts. It is this radiation that gives some of Europa's surface features their brownish-red colouring, salts and sulfur compounds chemically altered by the ceaseless bombardment. And here is the paradox. The radiation that makes Europa's surface one of the most hostile environments in the solar system also creates exactly the kind of chemicals that microbial life could use as food: oxygen, peroxides, oxidized salts. On Earth, these compounds are the currency of biological energy, the molecules that organisms break down to power their metabolism. Europa's surface is, in effect, a factory of potential nutrients, powered by Jupiter's magnetic field and stocked by billions of years of radiation chemistry. The raw ingredients for life are sitting right there, on the surface, exposed to the vacuum and the cold and the relentless radiation. The question, the central question, is whether any of those ingredients can find their way through 15 miles of ice to the ocean below. For a long time, this was the great puzzle. The ocean has water, it has heat, but does it have food? On Earth, nearly all life depends ultimately on sunlight. Photosynthetic organisms, plants and algae and cyanobacteria capture the energy of the sun and convert it into chemical energy, and everything else in the food chain depends on them. The entire biosphere, from bacteria to blue whales, rests on this foundation of captured sunlight. Europa's ocean has no sunlight. It has no photosynthesis. It has no plants, no algae, no cyanobacteria, no chlorophyll. And the Juno data showed that the cracks in the ice shell are too shallow to serve as pathways from surface to sea. The nutrients are sitting on top of the ice, produced by radiation, baked by the vacuum, frozen in place. The ocean is at the bottom, 60 miles deep, warm and dark and waiting. And between them stands 18 miles of solid ice with no cracks deep enough to connect the two. In January 2026, a team of geophysicists from Washington State University and Virginia Tech published a possible answer in the Planetary Science Journal. They described a process inspired by something that happens on Earth called crustal delamination. On our planet, slabs of dense crustal rock can detach from the surrounding material and sink into the mantle below, driven by their own weight. The researchers proposed that something similar might happen in Europa's ice shell. Patches of ice near the surface, enriched with radiation-produced salts and chemicals over millions of years, could become denser than the surrounding pure ice. Over geological time, these heavy patches might break away and sink, slowly descending through the shell under their own weight, carrying their cargo of nutrients downward like a slow, silent elevator. The process would be imperceptibly slow by human standards, but Europa has had billions of years for it to operate. Eventually, the nutrient-laden ice would reach the warm base of the shell, melt, and deliver its chemistry to the ocean below. It is an elegant idea, and it was published in the Planetary Science Journal in early 2026, but it remains a model. No one has observed it happening, and there is another question, perhaps even more important, waiting on the floor of that dark ocean. On Earth, the most productive ecosystems in the deep ocean owe nothing to sunlight. They are powered by the planet itself. At hydrothermal vents, fissures in the ocean floor where tectonic plates pull apart, superheated water laden with dissolved minerals erupts from the rock and pours into the freezing water above. The temperature difference is extreme, hundreds of degrees within a few inches, and the chemistry is extraordinary. Hydrogen sulfide, methane, iron, manganese, a cocktail of compounds that would be toxic on the surface, but that, in the deep ocean, forms the foundation of entire ecosystems. When researchers aboard the submersible Alvin first discovered these vents in 1977, 2.5 miles below the surface of the Pacific, they were stunned. Clustered around the smoking fissures were communities of organisms unlike anything in biology textbooks. Giant tube worms, some as tall as a person, their white tubes swaying gently in the current, their bodies packed with billions of chemosynthetic bacteria that converted vent chemicals into energy. Ghostly white crabs, blind, navigating by touch and chemical sense. Vast mats of microbes covering the surrounding rock, feeding on the chemical gradient between hot vent fluid and cold ocean water. An entire ecosystem, thriving in complete darkness, miles from the surface, entirely independent of the sun. The discovery fundamentally changed our understanding of where life can exist. It proved that sunlight is not a requirement. Energy and chemistry are enough. For years, the hope was that Europa's seafloor might have similar vents. If tidal heating warms the interior, perhaps it also drives geological activity on the ocean floor. Perhaps there are cracks and eruptions at the base of Europa's ocean, pumping warm, mineral-rich water into the cold water above, creating oases of chemistry in the darkness, just as they do on Earth. It was a compelling idea, almost too compelling, in the way that the best scientific ideas sometimes are. But in January 2026, a study led by Paul Byrne at Washington University in St. Louis cast doubt on this hope. The researchers used a combination of existing measurements and comparisons with Earth, the Moon, and other planetary bodies to estimate what conditions might be like beneath the ice. They calculated that Europa's rocky core has likely cooled significantly over the billions of years since the Moon formed. Unlike Earth, which still has a hot convecting mantle, driving plate tectonics and volcanic activity, Europa's interior may have lost most of its primordial heat long ago. The tidal heat that keeps the ocean liquid is generated primarily in the ice shell, not in the rock below. This means the seafloor may be cold and geologically quiet, a place of still, dark rock, with no vents, no eruptions, no chemical energy seeping upward into the water. Even Byrne himself was careful to note the limits of the study. No spacecraft has reached Europa's ocean, let alone its seafloor. The calculations rest on models and assumptions. Europa Clipper's measurements may reveal a different picture. But the study serves as a useful corrective to the most optimistic scenarios. It reminds us that wanting something to be true does not make it true, and that the search for life on Europa must be conducted with the same rigour and honesty that characterises the best science. If the seafloor is cold, life on Europa would need to find its food from above, from the slow rain of nutrients sinking through the ice, rather than from the warmth of the planet's interior. Any life in that ocean would need to be extraordinarily frugal, surviving on whatever small supply of chemistry drifts down through miles of ice over geological timescales. It would need to be patient in a way that defies human comprehension, measured not in years or centuries, but in epochs. But life on Earth has demonstrated again and again that patience is one of its most remarkable qualities. Consider Lake Vostok, buried beneath 2.5 miles of Antarctic ice, sealed from the surface for perhaps 15 million years. When Russian scientists spent decades drilling through the ice sheet to reach it, many in the scientific community expected to find nothing. The conditions seemed too extreme, too isolated, too hostile. The lake had been cut off from sunlight, from the atmosphere, from every external source of energy, for longer than the entire genus Homo has existed. When they finally reached the lake water in 2012, they found microbial life. Organisms that had persisted in the dark under crushing pressure, cut off from the sun and the atmosphere for millions of years. They had not merely survived, they had continued. The discovery was a quiet earthquake in the field of astrobiology, because it showed that isolation and darkness and cold are not, by themselves, enough to prevent life from persisting. Consider the deep rock of the Earth's crust. Kilometres below the surface, in cracks and pores in the bedrock, far below the reach of any root or any ray of light, microbes have been found living on nothing more than the chemical energy released by water reacting with minerals in the rock. A process called serpentinization, in which water interacts with iron-rich minerals and produces hydrogen gas, provides just enough energy for these organisms to survive. They grow so slowly that some may divide only once every 1,000 years. A single generation of these microbes spans the entire history of Western civilization. They exist in total darkness, under enormous pressure, in environments where the concept of a day or a season has no meaning. They are alive in the barest, most elemental sense of the word, and they have been alive in those dark cracks for a very long time. These examples matter because they redraw the boundaries of where life can exist. Every time scientists have declared a place too extreme, too dark, too cold, too pressurized, too isolated for life, life has been found there anyway. Not complex life, not whales or trees, but microbial life, simple, tenacious, indifferent to the conditions that would kill any organism we consider sophisticated. The lesson is consistent and humbling. Life needs liquid water, a source of chemical energy, and time. Europa has all three. Whether it has life is a separate question, but the argument that it cannot have life because the conditions are too extreme is an argument that Earth's own biology has refuted, repeatedly, in some of the most inhospitable places on our planet. If there is life in Europa's ocean, what might it look like? The honest answer is that we have no idea, and anyone who claims otherwise is speculating beyond the evidence. But we can reason from what we know. It would almost certainly be microbial. The energy available in Europa's ocean, whether from nutrients sinking through the ice or from faint geological activity on the seafloor, would be far too scarce to support complex organisms. There would be no fish, no kelp, no coral. The ocean, if it is inhabited at all, would be home to something far simpler and far more ancient in its design. These organisms might drift in the dark water, feeding on whatever trace chemicals filter down through the ice. They might form thin biofilms on the underside of the ice shell, clinging to the boundary between solid and liquid, eking out existence in the narrow zone where nutrients accumulate before being absorbed into the ice above. They might cluster around warm spots on the seafloor, if any exist, or around the underwater snow at the base of the shell, where the chemistry is richest. They might use hydrogen as an energy source, or sulfur, or some compound we have not considered. They might store their genetic information in DNA, as all life on Earth does, or in some other molecule entirely. Life that arose independently on Europa would owe nothing to our biology. It might be recognizable to us only by its behavior, its tendency to grow and respond and reproduce, and not by its chemistry or its form. We might need to learn to see it before we could find it, or it might not be there at all. This is the possibility that must be stated plainly without flinching. Europa may have every ingredient for life, water, chemistry, energy, time, and still be empty. We do not know how life begins. We know it happened on Earth roughly 4 billion years ago, but we do not understand the mechanism. We cannot reproduce it in a laboratory. We do not know whether it was a near certainty given the right conditions, or a cosmic accident so unlikely that it has happened only once in the history of the universe. Europa's ocean may be vast and ancient and chemically rich, and utterly, completely lifeless, a dark sea with no one in it. That would be a discovery too, a profound one. Because if Europa has everything life needs and life did not arise, it tells us something important about how rare biology might be. It tells us that water and chemistry and time are not enough, that something else is required, some spark or some convergence of conditions that we do not yet understand. And it tells us, perhaps, that the silence of the universe is not a puzzle to be solved, but a reflection of the way things are. Either answer, life or no life, would reshape our understanding of our place in the cosmos. That is why Europa matters, not because we know the answer, but because we are finally in a position to ask the question properly. We are about to look. In October 2024, NASA launched a spacecraft called Europa Clipper from Cape Canaveral on a Falcon Heavy rocket. It is the largest spacecraft the agency has ever built for a planetary mission, spanning 100 feet from the tip of one solar panel to the other, longer than a basketball court. It carries 9 scientific instruments, cameras that will photograph the surface in unprecedented detail, spectrometers that will map its chemical composition, a magnetometer that will probe the ocean's depth and salinity, a thermal imager that will search for warm spots on the surface, and an ice-penetrating radar that can see through the frozen shell. It is, in every sense, the most capable machine we have ever sent to investigate another world's ocean. The journey to Jupiter takes 6 years. Europa Clipper used a gravity assist from Mars in March 2025, swinging past the red planet to gain speed. In December 2026, it will fly past Earth for a final gravitational boost. Then it will coast outward through the solar system, past the asteroid belt, through the vast emptiness between Mars and Jupiter, falling slowly toward the largest planet in our neighborhood. It will arrive at Jupiter in April 2030, where it will perform a flyby of Ganymede, using that moon's gravity to slow down enough to enter orbit around Jupiter. Over the following 3.5 years, it will make 49 close flybys of Europa, swooping as low as 16 miles above the surface, scanning and measuring and listening with every instrument it carries. Each flyby will take the spacecraft through the most intense radiation in the solar system, and each time its instruments will be sheltered inside a titanium vault designed to protect them from the bombardment. The spacecraft will dive in, gather data, and retreat, again and again, like a swimmer braving cold water in short, determined bursts. One of the most important things it will search for is plumes. In 2012 and again in 2016, the Hubble Space Telescope detected what appeared to be jets of water vapor erupting from Europa's surface, rising more than 100 miles above the ice before falling back. The observations were at the very edge of Hubble's capabilities, and the scientific community has debated their reality ever since. Some researchers are confident the plumes are real. Others believe the detections may have been artifacts. If the plumes are real, they are extraordinary. They would mean that the ocean, or pockets of liquid water trapped within the ice shell, is reaching through the cracks and venting directly into space. If Europa Clipper can fly through one of these plumes, it could sample the ocean without ever landing. It could analyze the chemistry of the water. It could search for organic molecules, amino acids, the building blocks of life, in a spray of ocean mist erupting from another world. The encounter would last seconds. The implications could last centuries. Even if the plumes prove elusive, the ice-penetrating radar will look through the shell, mapping its internal structure, searching for pockets of liquid water that may exist within the ice itself. Scientists believe there could be lakes trapped inside the shell, reservoirs of meltwater sitting miles below the surface but miles above the ocean. If these lakes exist, they could be places where surface chemistry and ocean chemistry mix, windows into Europa's water, closer and more accessible than the ocean itself. Europa Clipper is not officially a life detection mission. NASA is careful about that distinction. Its stated goal is to determine whether Europa has the conditions necessary to support life, the water, the chemistry, the energy. But if its instruments find the right combination of organic molecules in a plume of ocean spray, the distinction between detecting conditions for life and detecting life itself may become very thin indeed. The spacecraft carries something else as well. Engraved on a tantalum metal plate inside the spacecraft's radiation vault is a poem by the American poet laureate Ada Limon called In Praise of Mystery. On the same plate, on the side facing inward, are the names of 2.6 million people from around the world who signed up to have their names carried to Jupiter. And on the outward-facing side is the word water, written by hand in 103 different languages. It is a message from Earth to Europa, from one world of water to another, from a species that has spent its entire existence asking whether it is alone, sending its question across 1 billion miles of darkness, inscribed on a metal plate carried by a machine, aimed at a moon it has never touched. Europa is not the only ocean world in our solar system. Enceladus, a tiny moon of Saturn barely 300 miles across, also hides a liquid ocean beneath its icy surface. In 2005, NASA's Cassini spacecraft discovered enormous geysers erupting from fractures near Enceladus's south pole, shooting jets of salty ice particles hundreds of miles into space. The fractures were warmer than the surrounding ice by tens of degrees, and the plumes were spectacular, great curtains of ice particles backlit by the distant sun, rising from the surface and dispersing into Saturn's E-ring. Cassini flew through those plumes multiple times over the following years and tasted the water. It found sodium chloride, common table salt, dissolved in concentrations similar to Earth's oceans. It found organic molecules, complex carbon-containing compounds. It found tiny silica particles, nanometers across, that could only have formed in water heated to at least 90 degrees Celsius at high pressure, strong evidence of hydrothermal vents on the seafloor. Enceladus, this tiny, unremarkable-looking moon, had an ocean with hot water, salt, and organic chemistry. It had, in other words, every ingredient that life requires, and there may be others. Ganymede, Europa's larger sibling, likely has an ocean buried deep beneath its ice, sandwiched between layers of ice at different pressures. Titan, Saturn's largest moon, has lakes of liquid methane on its surface and may have a water ocean below its icy crust. Even Pluto, that cold, distant world at the edge of the solar system, may harbour a liquid layer beneath its nitrogen ice, kept warm by the slow decay of radioactive elements in its rocky core. The solar system, it turns out, is full of water. The dry, rocky inner planets, Earth, Mars, Venus, Mercury, are the exception, not the rule. Most of the liquid water in our solar system is hidden beneath ice, in the outer darkness, far from the sun. We spent centuries assuming that life required sunlight and a surface ocean and a warm, sheltered planet like our own. The discovery of these ocean worlds suggests that we may have been thinking about it backwards. Perhaps the most common habitable environment in the universe is not a sunny surface. Perhaps it's a dark ocean, sealed beneath ice, warmed by tidal forces or radioactive decay, existing in complete independence from any star. If that is true, the galaxy may be full of life, and almost none of it would be visible from the outside. And so we arrive at the question that has been waiting beneath everything we have discussed tonight. The oldest question, the simplest question, the one that children ask and that scientists have spent lifetimes trying to answer. Are we alone? It is a question that has been asked in every language, in every culture, in every century of recorded human history. We have looked for the answer in myths and religions, in philosophy and mathematics, in the static between radio stations and the spectra of distant suns. In 1961, the astronomer Frank Drake wrote an equation to estimate the number of communicating civilizations in our galaxy. It was not really an equation. It was a way of organizing our ignorance, a list of all the things we did not know, arranged in a row and multiplied together. More than 60 years later, most of the terms in that equation remain unknown. We still do not know how common habitable planets are. We still do not know how often life arises. We still do not know how often it becomes intelligent, or how long civilizations last. The equation has not been solved. It has simply waited patiently for data. Europa may provide some of that data, not all of it, not the final answer, but a piece of it. A single, crucial data point. If we find life on Europa, we will know that life arose independently at least twice in one solar system. And if it arose twice here, in two very different environments, separated by hundreds of millions of miles, then the implication is staggering. Life is not rare. It is a common outcome of the right chemistry and the right conditions. The universe may be full of it. We have searched for the answer in radio signals from distant stars. We have scanned the atmospheres of exoplanets for chemical fingerprints of biology. We have sent rovers to Mars to dig in the soil and taste the air. And so far we have found nothing, not a single confirmed sign of life anywhere beyond Earth. The universe, as far as we can tell, is silent, but perhaps we have been looking in the wrong place. Perhaps the answer is not written in starlight or radio waves. Perhaps it is written in water, in an ocean sealed beneath the ice of a small moon, orbiting a gas giant in the cold outer reaches of our own solar system. The ocean waits, as it has waited for billions of years. Whatever is down there, if anything is down there, has been there longer than we have existed as a species. It was there before the dinosaurs, before the first fish, before the first cell divided in a warm, shallow pond on a young blue planet 400 million miles away. It was there when the sun was younger and fainter. It was there when the Earth was still molten. And it will be there long after we are gone, unless we find a way to reach it. Somewhere right now, as you listen to this, Europa Clipper is moving through the darkness of deep space. Its solar panels are stretched wide, its instruments are quiet, its cameras are dark. It is falling toward Jupiter, pulled by gravity, guided by mathematics, carrying a poem and 2 million names and 9 instruments designed to answer a question that humanity has been asking since it first looked up at the night sky and wondered. In 2030, it will arrive. It will open its eyes. And for the first time in history, we will begin to look carefully and systematically for the conditions that might allow life to exist in an ocean we have never seen, on a world we have never touched, beneath ice we cannot yet penetrate. And if what we find there suggests that life is possible, then someday, perhaps not in our lifetime, but someday, we will send something else, something that can land on the ice, something that can drill or melt or bore its way down through 18 miles of frozen silence, something that can descend into water that no light has ever touched and look around. Engineers at NASA's Jet Propulsion Laboratory are already designing such machines. A snake-like robot called Eels, built to navigate ice crevasses, concepts for nuclear-powered probes that would melt through the shell over months or years, trailing a communications tether behind them. These machines are decades away from flight, perhaps generations, but they are being designed right now by people who know they will probably not live to see the results of their work, and there is something quietly remarkable about that, about the willingness to spend a career building a machine that will answer a question after you're gone. Whatever we find in Europa's ocean, even if it is nothing, will be one of the most important discoveries in the history of our species, because we will have opened a door that has been closed for 4.5 billion years, and we will have looked inside. Maybe your eyes are heavy now, maybe the room has gone quiet, but somewhere out there, right now, a machine is falling through the dark toward Jupiter, carrying a poem and a question, and 2 million names, and beneath the ice of a small, cracked, radiation-scarred moon, an ocean is waiting, as it has waited for longer than anything on Earth has been alive, patient, silent, and full of whatever it is full of, which we do not yet know, but which we are finally on our way to find out. Thank you for listening to Strindberg's Space Stories. If this story gave you something to carry into the night, subscribing truly helps us keep making these, and I'm grateful for every one of you who does. Take care of yourself, sleep well, and keep looking up. Good night.